Kia ora. Welcome to week 2 of 162.04. In the first lecture this week we're going to look at direction fields, which is a way of getting information about solutions to a differential equation without actually solving it, without using calculus. And even if you can solve the differential equation, it's a very useful way of visualizing what this differential equation is trying to tell you. So let's start with the general first order differential equation, dy dx equals f of x and y. And just think that the right hand side there might be quite a complicated function. So its value varies as you move around the xy plane. And what this differential equation says is if there's any solution curve that passes through some particular point, xy, what information do I get from the dE? Well, it says that the slope, dy dx, at that point must be equal to f of x and y. So I know at least what the slope of the equation is. It doesn't tell me where it's going next, but it tells me in which direction it's going. But that's true for every point. That means I can attach a little stick or arrow to every point in the xy plane, telling me what the slope of any solutions would be if they pass through that point. So let's see how that would work for a nice simple one, where it's easy to work this out by hand. We'll do this favorite equation, dy dx equals 2y. And first let's look along the line y equals 0. Well, on the line y equals 0, the right hand side is 0. That means the left hand side is 0. That means the slope must be 0. So the sticks are a little bit hard to see, but they're little sticks of slope 0. On the line y equals a half, 2y is equal to 1. That means dy dx must be equal to 1. So I draw little sticks at a 45-degree angle. Any solution that passes through that point must be having slope 1. And at y equals 1, the slope must be 2. So a bit steeper. At y equals negative a half, 2y is negative 1, the slope must be negative 1. At y equals negative 1, the slope must be negative 2. So this was fairly easy to draw the direction field by hand because the right hand side was a fairly simple function. For a more complicated one I'd have to use a computer. But you can already see that the solution curves, what they're going to look like. There's going to be one along here, its tangent is horizontal. The other ones have to be smooth curves that always point in the direction, always tangent to the direction field. So I can see that they must be getting steeper and steeper and steeper. For example, if y is positive, that means the solution must be increasing. Then y is bigger. That means it's increasing faster. So I can already get that the solution curves must be concave up. So you can see how the solution to a differential equation like this must be a family of smooth curves that fills out the plane. I think this is summarized on the next slide. Here we are, the direction field. It's the xy plane with a small arrow of slope f of x and y attached to each point. The graphs of solutions are curves that are tangent to those arrows. Anywhere f of x and y is 0, any solution passing through that point must be horizontal. If f of x and y solutions must be increasing. If f of x and y is less than 0, solutions must be decreasing. So let's draw the direction field for a slightly more complicated one, dy dx equals x plus y. Still simple enough that I can do it by hand. Well, it's not going to look that pretty, but I'm going to do the best I can. Well, there's two ways you could approach this. You could set up a grid, say a 5 by 5 grid, take every x and y pair in the grid, and then draw a little slope attached to it. But I'm going to be a little bit clever because I noticed that on the curve x plus y equals 0, then dy dx is 0. So if I just sketch in a little dotted line there, that's the line x plus y equals 0. Y equals negative x. Everywhere on there, the slope of any solution curve passing through that point must be horizontal. Similarly, on the curve x plus y equals 1, the slope must be 1. So I draw a little line of slope 45 degrees. On the line x plus y equals 2, the slope must be 2. Here's x plus y equals -1. The slope must be -1. That's highly suggestive. On x plus y equals -2, the slope must be -1. Whoops, sorry. Slope must be -2 on x plus y equals -2. So that's an attempt to do the start of the direction field for that differential equation. And I can see what the solutions are going to look like. There's going to be one solution that's in fact x plus y equals -1. The other ones must look like this. Horizontal, slope 1, slope 2. Horizontal there, slope 1 there, slope 2 there. Horizontal there, slope 1 there, slope 2 there. Below this line, the slope is less than -1, so they'll be going down steeper and steeper and steeper. And that looks very similar to what we had before. So I'm just going to switch over here and go into MATLAB or Octave and draw a direction field using MATLAB. In fact, on this laptop it's Octave, but it's the same for this purpose. So to do that, I need to set up two arrays that are going to hold the x and y coordinates of all of the points where I want to draw an arrow. So I'll call that big X and big Y. The command for that is meshgrid, and you give it two vectors, a vector of x values and a vector of y values. So for both of them I'll use starting at -2, increasing in steps of 0.2 up to 2, and the same for y. Now those will be big arrays of size 20 by 20, so I don't want to print them out, so I put a semicolon at the end. Yes, there we are, 21 by 21 array. Now the command to draw the direction field is quiver, and you give it the x and y points. Now I have to give it the x and y components of the vector at each point. So for the x component, since I want slope f of x and y, I want my x component is going to be 1 and my y component will be f of x and y. So I just go big array of 1s of the same size as x, and then my slope, which is in this case x plus y. Can't see the graph because it's behind, so SHG stands for show graphics. And there it is, there's the direction field. So that's not only significantly neater and more accurate than the one I drew, I also get a lot more points. If you put too many points in, of course, it starts to become impossible to see the little arrows. But that's pretty compelling. And in this case, since I do know this formula for the solution curves, I can actually overlay them. So I want to go hold on to stop the previous graph being destroyed, and then plot. I need a vector of x values. So I want very small spacing now because I'm going to join these points together with a smooth curve. So I'll do spacing of 0.01. And then plot x. And my solution was e to the x minus 1 minus x. Why didn't it work? Read back at the commands. Oh yes, here's my error. X went from 2 up to 2. That's not very many points. X wants to go from -2 in steps of 0.01 up to 2. Semicolon. Plot x e to the x minus 1 minus x. Show graphics. And there we go. There's a nice solution curve. Everywhere tangent to the direction field. Now if I want to plot lots of solutions, say 20 of them, or if I want to plot a solution that goes through every point, I don't want to do those all by hand. I want to use a loop. So I could go for a equals -2 in steps of 0.2 up to 2. Plot x against a e to the x minus 1 minus x. In the for loop, show the graphics. Now that looks a bit weird, but that's because some of the y values have gone up to negative 20. So I need to zoom in a little bit, which you can either do interactively or you can use the axis command. Let's go from minus 2.5 up to 2.5 in x and minus 2.5 up to 2.5 in y. There we go. Nice family of solution curves telling you a lot about what that solutions of that differential equation are doing, and you can see how all of them are tangent to the direction field. Okay, now there's a second thing we can do from a differential equation without solving it, and it's particularly useful for differential equations of the form dy dx equals f of y, where there's no x appearing on the right hand side. And in fact there's no x, there's none of the independent variable appearing anywhere in the differential equation. That comes up a lot in applications, and that's called an autonomous differential equation. That means self-acting. Now the definition is a value of y, which I'm going to call y star, is called a fixed point if f of y star is 0. And the reason that's significant is that then that constant value of y star will be a solution of the differential equation. And just before I go on, there are other names for fixed points. They're also called stationary points of the differential equation, or equilibrium points, or critical points. And unfortunately, you do hear all of those different names fairly frequently as well. Why is y star a solution? If you just take this as a trial solution, y of x equals y star, a constant solution, so its graph is just a horizontal line, well, f of y star is 0, and the derivative of a constant is 0, so it does satisfy the differential equation. Okay, let's work out the equilibrium or fixed points for this one. Dy dx equals y minus y cubed. That means I have to solve y minus y cubed equal to 0. That's a polynomial, it's a cubic polynomial. So to solve polynomials, you want to factor them. Got a common factor y. And I can factor 1 minus y squared as well into 1 minus y, 1 plus y. So there's three solutions, y equals 0 and plus or minus 1. So this differential equation has three fixed points, 0, 1 and negative 1. And notice that I didn't have to do any calculus to find that. I just had to solve this algebraic equation, y minus y cubed equals 0. So that means I can draw some solutions already. Y equals 1 as a solution, y equals 0 as a solution, y equals negative 1 as a solution. What do the other solutions do? Well, I could draw the direction field, and that's actually a really good idea, but I just want to do it a slightly different way this time. What I want to do is look at the sign of y minus y cubed, because if y minus y cubed is positive, that means dy dx is positive, which means the solution curve must be increasing. So what's the sign of y minus y cubed? Well, to work that out, it would be helpful to have a graph of y minus y cubed. So I'll just draw that on the side over here. And it helps to know that I already where the zeros are, when y is negative 1, 0, or 1. And what does the graph of this cubic look like? It's got 3 zeros. It's got a negative coefficient in front of the y cubed. It's going to look like this. So that means whenever y is between 0 and 1, y minus y cubed is positive. So everywhere here in this region here, which I didn't really want to draw in there, everywhere in here in this region, the solution must be increasing. Now when it's close to y equals 0, y minus y cubed is very small, so it has to be increasing slowly. So I see that the solution curves in between there must be increasing very slowly, then more quickly, and then more slowly again. And they'll all look like that because nothing depends on x. Doesn't matter which x value I start at. Likewise, when y is between 0 and -1, you can see from the little graph on the right that y minus y cubed is negative. I must be decreasing. These will all be solution curves of the differential equation. When y is bigger than 1, y minus y cubed is negative. So I must be decreasing, but I can't cross that line y equals 1, because there I would have to have a horizontal tangent, and I've already got a solution there. So I must just get closer and closer to it. Same down here, decrease, 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 never come back. So even for a more complicated differential equation, this one's non-linear, I can work out what the solutions are going to look like everywhere in the plane.